All right. Hello, everybody. My name is Jacob Moss, and I'm here today with Ronan O'Neill and Jordan Miller. And this is going to be our Physics 212 project number 2, where we'll be discussing the buoyancy topic. To begin, I'm just briefly going to go over the formatting of this presentation. Today, we're going to be approaching this problem with our frequently used explanation task formatting that we've been made familiar with over the course of this class in the homework assignments, studios, lectures, and get ready activities. What this means is that we're going to be breaking this question into 3 main sections, starting with the building blocks, where we'll be going over the fundamental principles and concepts necessary to the understanding of the overall problem, creating a foundation for our reasoning. This is going to be followed by the reasoning section, where we're going to be going over the key steps and points that take you through the building and understanding of the problem. And then finally, we're going to be tying everything back together with the conclusion, where we state our conclusion clearly and ensure that the subject makes entire sense. Alrighty, the problem that we have selected to discuss today is the buoyancy subject. We have been tasked with creating a model for force due to pressure of a displaced fluid on an object immersed in said fluid. This force is what we know as buoyancy, and we will be using this previously explained model in order to explain real-world examples, such as why one object may float in a liquid while another immersed in this same liquid may not. Very vague in nature, of course, but we will be providing explicit examples later on in our presentation in order to support our reasoning. One last thing that we do need to discuss before beginning is our physics model. So far in this course, 211 and 212, we have dealt with numerous forces that we may be able to put to use here. However, nothing that we have gone over so far has included pressure, which is the key concept setting this problem apart from what we already know. We will be explaining the properties of pressure and the relations to the forces in this problem in order to expand our model to include pressure and more specifically buoyancy related problems. Alrighty, let's get started on our reasoning section. To begin, I'm going to start by giving a brief definition of buoyancy. Buoyancy is known as the upward force exerted on an object immersed in a floating in a fluid like a liquid or a gas due to the pressure differences acting on the object's upper and lower surfaces. This can be loosely defined conceptually with the equation force of buoyancy is equal to the force up subtracted by the force down. A more complete example of this equation would be the force of buoyancy is equal to rho times g times Vf, where rho is the density of the fluid being submerged into, and Vf is the volume of the liquid displaced by this object. We're going to be going into further detail on the steps to go between these two equations further in the video, but for now it's important to just understand that this equation is reliant on the relationship between the object's density and the fluid's density. The biggest takeaway from all this is that the density of the object plays the lead role in buoyancy. If the density of the object is greater than the liquid that it is being submerged into, it is going to sink and vice versa. I will now be turning the presentation over to Ronan to go over our reasoning, and thank you all for your time.
Hello, my name is Ronan O'Neill, and I'm going to be doing the reasoning portion for our project on the buoyancy problem. So right here I have a little diagram. We've got a ball that's sitting under the water, just under the surface of the water at height h, with pressure acting on it, and I'm just choosing a ball for this specific diagram, but it doesn't have to specifically be a ball. It can be a square, it can be any object that's sitting under a liquid. What we're trying to figure out is our force. We want to figure out the buoyancy force. So we can do that using these 4 equations we have here. So the first 2 equations, we've got pressure equals height times density, which is represented with rho, times gravity. Then we also have pressure times area equals force. And then what we can do with these 2 equations is we'll take the pressure times area equals force. We're going to substitute in h rho g for pressure. When we do that, we get this equation right here. Force equals h rho g times a y hat. The reason we have the y hat attached to the area right there is because the pressure is only acting in one direction, and that is going to be the y direction. It's acting upwards on our object. And then from this, we can simplify it and get F equals v rho g y hat, where v is our volume. The reason that we can substitute in volume there is because in this part right here, we have height times area, and the height times the area of an object is going to give us the volume. So we just do that to simplify it. And using this, we can get the force that's acting upon the object. And basically what this is telling us is, specifically for this problem, the force that we get from that is equal to the weight of the liquid that has been displaced. And that makes sense when we think about volume times density times gravity. That is basically just giving us the weight of our object. Now, when we figure this out and we can figure out what the force, the buoyancy force of our object is, this can tell us will our object sink, float, or neither. So right here we've got force of gravity is greater than the force of buoyancy. So when the force of gravity is greater than the force of buoyancy, we know that our object is going to sink because that force of gravity, since it's stronger, is going to be pulling the object down. Now, we know our object is going to float when the force of gravity is less than the force of buoyancy, and that's because since the force of buoyancy is overcoming that force of gravity, it is going to stay up. And I have that represented here with a free body diagram where we've got force of gravity going down and then the force of buoyancy acting upwards upon our object. And since our vector of buoyancy force is greater than our vector of gravity force, our object is going to be floating. And then finally, we have force of gravity equals the force of buoyancy. When we get that, our object is going to be doing neither of these things. And I have that represented in this drawing right here, where the object is sitting just under the water, but it's not sinking towards the bottom. And since it's sitting right under the water, it's technically not floating either. So that's what you get when your force of gravity equals your force of buoyancy.
Hi, my name is Jordan Miller, and I will be handling the conclusion section of me, Jacob, and Ronan's project. So in conclusion, the question of whether or not an object floats or sinks in a medium is determined by the differences in the object's density and the medium's density, whether that be the water or the air or whatever it's being placed in. If the object's density is less than that of the medium's density, it will float. And if it is greater than that of the medium's, it will sink. An example of that is what we have on the left here, a party balloon. A balloon such as this will be filled with helium and will float. This is because the gas helium is less dense than the surrounding medium, in this case being air, and therefore it will float. This is also the reason when you're filling a balloon with air that it is neutrally buoyant, and therefore you might ask, well, if it's neutrally buoyant, it's not going to sink. It shouldn't sink. Well, that's because now the only force acting upon it is gravity. Therefore, it will sink. Another example of neutral buoyancy, since we already talked about that just a second ago, is a submarine. As you can see in the diagram I have on the board, submarines have what's called a ballast tank, and it is seen in the image. It takes in more water to become more dense, allowing it to sink. And to float back up, they put air into the ballast, making it less dense than the water, allowing it to rise or float. When they level out, they have both a mixture of air and water so that they have an equal density to the surrounding medium, allowing them to stay in place and not rise or sink. This is why they can continue at the same level in the water. In terms of sinking, a very simple example that I have this slight diagram, you could say, is a penny being tossed into a fountain. The copper that the penny is made of is a more dense material than the water, therefore having it sink to the bottom. The boat is similar, but a little more complex. So a large boat has the bottom half filled with air. The bottom half of the boat is filled with air, and although the material of the boat is actually more dense than the water, that the material of the boat that's built of, the air in the lower half, which is less dense than the water, keeps the boat overall buoyant on the surface of the water. So the air within it, even though the actual material of the boat is made of a material that's more dense, therefore it should sink, the air inside the lower half, which is less dense, allows it to float. Additionally, our conclusion does make sense. We are able to confirm the use and the practicality of Archimedes' principle and the buoyant force formula. Additionally, the information presented by Jacob, Ronan, and myself explains the what, the why, and the how for buoyancy. With a model and real-life applications, we can confidently conclude that it is understandable. Thank you.